Okay, we're back with Chapter 3, Fluid Statics. This section is going to cover Section 3.6 on buoyant forces and the buoyancy equation. So we're going to describe the physics of the buoyancy equation and the meaning of the variables that appear in the equation. This is actually a pretty simple section. It's not going to take us too long, but it's a very powerful concept. In a separate recording, I will do an example problem applying the buoyancy equation. So let's skip ahead to the section on buoyancy through the sections that we've already done. And start here, calculating buoyant forces. I'm going to kind of start with the conclusion. The conclusion is that all objects and fluids, whether they're gas or liquids, have buoyant forces on them. And Archimedes' principle is the governing principle upon which we understand buoyant forces, or upon which we can understand these. And the primary conclusion is that the buoyant force is going to equal the weight of the displaced fluid. And a good example of this is if you have a glass of water, say, or soda, and you take some ice cubes, say 3 or 4 ice cubes, and you place them into the top of the glass, we know that ice floats. It floats because there's a buoyant force on it. And if you put the ice cubes in there and you just let the glass sit there for a minute, everything will come to rest. And at that point, the objects are static, and it's a fluid statics problem. And there is a buoyant force that is pushing up on the ice cubes that is equal and opposite to the weight of the actual ice cube. And so the buoyant force actually equals the weight of the fluid that's displaced by the ice cube. So if you place an ice cube, a series of ice cubes or a set of ice cubes into a glass, you can notice that the level of the fluid will rise. And so every object that you put in, whether it's partially or totally submerged in that fluid, the fluid level will rise. So it's that weight of that fluid that's displaced that is equal to the buoyant force, and we'll show that in a minute. The other point that I want to make is that the buoyant force acts at a point called the center of buoyancy. This is similar to the concept of the center of pressure when we looked at flat panels. And this is actually located at the center of gravity of the displaced fluid. So let's take a look at this. Here's a diagram. I've actually enhanced it a little bit with some vectors. I'll get to that in a minute. But let's take a look at the left-hand side first. There's a couple of different ways to look at this. And so here we have an arbitrary object in the fluid. And one way to think about this is through the hydrostatic pressure distribution that we've been talking about. And the first thing to note is that we already know that deeper in the fluid, the pressure distribution, the pressure force, compressive pressure force will be greater. And so these vectors are actually larger. These arrows are larger than the arrows on top. And so there's a net force upward, and that is the buoyant force. So in order to derive this force, we actually have to use some concepts from section 3.5. And we can note that the pressure distribution on the top surface is going to be the weight of this water above the object. And so that's just a specific weight. The weight of this chunk of fluid of AEFC is just gamma times that volume, the volume of that water and or fluid. And the force on the bottom is greater. We know that the pressure is greater, and so the force per unit area is greater, and the force is greater. So we have a larger upward force. You can see this vector is a little bit longer. And that's equal to, if you can imagine some extra volume here, if we were just able to magically remove the object for a second, we would have this shape that would be actually ADC. There's a D underneath this vector, EF. And so we've got basically the weight of this fluid, if we replace the object with fluid, plus the original fluid we had, VA. So we've got a little bit larger volume we have to add basically the volume of the body. This volume, A, B, C, D, is just the volume of the object in the fluid. So it's those two forces. The buoyant force is going to be greater on the bottom than on the top, and we can think of it either in terms of a hydrostatic pressure distribution or in terms of the forces. And of course, we can see that when we just simply calculate the buoyant force, then FB as being F up minus F down, we can see that this is basically a very simple equation. VB plus VA for the upward force, and we're going to basically subtract off the area of the fluid above it. So this just becomes, the buoyant force becomes the weight of the displaced fluid. The weight, and basically that's equal to the fluid that would occupy the object. So let me read this. The net force or buoyant force equals the weight of the liquid that would be needed to occupy the volume of the body. So that is this particular volume right here. It's VB is the volume of the body. So so that's the buoyant force, and we can look at it for a partially submerged body as well. It's the same principle. In the case of a partially submerged body, we don't have the entire body submerged. So we're not going to consider the whole volume of the body. We're only going to be considering the volume of the body that's displaced. And you can see that if we toss this thing, this might be an ice cube in a cup, if we put this thing in to the fluid, it's going to displace the same amount of fluid as is the volume of the body. And that weight, gamma, times the volume of the submerged portion of the body is going to be the buoyant force. So the buoyant force is equal to the weight of the liquid needed to fill basically this volume of ADC. That's really all that there is to the buoyant forces. So when you're thinking about buoyant forces, you need to think about volumes primarily. If you're in a fluid that's all of the same type, if it's just a constant gamma, then the only thing you need to think about really are volumes, the volume of that's being displaced. So in homework problems, typically you're going to be given bodies that are either submerged or partially submerged, and if you're able to find the volume of that total volume that's submerged or just the partial volume that's submerged, you're going to be able to easily calculate the buoyant force just by multiplying it by the gamma of the fluid. So that's it. In the next video, the accompanying video, I'll solve this problem here.